So this is our last session in our 3-day program, and today we are about to talk about these nice tools developed by different groups. And the first talk will be Jaroslav with the boot GAC Python. So Jaroslav, the
Yes,
floor is
thank you.
yours.
Thank you. I would like to present one Python package which have been developed. My former student, Marek Stodola, he's now in some commercial company, so he's not either work on it. So it's called boot GAC, and it's about geometric algebra of conics, but the algebra is designed in a bit of different way by using both periodicity, and there is also the both periodicity. I will explain. I will explain in detail, and also this is open. This is free on GitHub, and uh, he already prepared some procedures for the fitting ellipses and generally conics, but it's closed because it needs to be a bit of improved. But if somebody from you will be interested about it, it's very easy to share with you. It's working, but it's not in a completely publishable form. So I prepare. Sorry, maybe I did wrong. Yeah, no, I did right. I prepared just the my PyCharm to show you exactly how it works with set of examples. So at the first, you can see that intro. So at the first, and you can see I just add some points uh, to to some list, and then just by by get conic by points, I will receive my conics, and the first I will show you how the representation of the conics looks like. This is different because the conic in my setting it's a matrix 4 times 4. I will explain later what it's mean. This is what I mentioned, the both periodicity, and this is one advantage of this. And now I will show you how it looks like. It looks like in the draw, and you will see these points, and these points, for example, these points belongs to some hyperbole, and the red are the points, and the blue points, this is only drawing of the conics, which is not so important. This is just to see how it looks how it looks like general. But what is important, we always draw and compute any lines and any circles which belongs to the conics. So in the case of hyperbola, we always compute these two lines which are tangent to hyperbola. The next example, it's you can see you can use the translator in CRA and rotor, and by this the next point are computed, and the resulting conic will be ellipsis now. So we will see the part of the ellipsis. So it yeah it just so you have a you get conic by points, and now the opposite direction. If you would like to initialize some ellipse, hyperbole, parabole, you just specify the internal parameter of it, and you can easy set it. So if I show it, it's ellipses. And now let me explain a bit. This is what we did it mostly because we would like to classify the ellipses by the objects which are not which are from CGA. This is our approach because we would like to use the conformal geometric algebra to describe some properties of ellipses, and especially the transformation between ellipses. So this package is designed exactly for it. So any ellipses is is uh, is computed and is represented as a pair of lanes and a pair of circles. And now, if we have, I will talk about it later. And if you are talking, if you are thinking about the transformation which maps one ellipse to the second ellipse, this is some special kind of transformation. We can, in the same kind, we can think about the transformation which map the inner circle to the inner circle, outer circle to the outer circle, and one of these lies to one of these lies. So we have just two conformal transformation and one linear transformation, and this three transformation described maybe under describe the transformation itself. I'm not sure about it. It's open. It's there are a lot of similar open questions for us. So so now there are some more, and I will show there are all the rotation and translation are implemented, so we can play with it. So for example, here you will see the, I think you will see the ellipses and ellipses which have been rotated to somewhere. So you have in one picture you have two ellipses and one is rotated and translated to each other. So it, it works, and this is one of your goal. And now mhm, now I can show you for just the last picture where I will put more these conics to one to just to show something which will be very mess. So nice. No, yeah, you know, yeah, a lot of things in it. So yeah, you can do everything of from it. And also, if you have this connects which have been initialized to the software, you can ask about the parameters. So just by ask parameter of connects, you will see center, axis, axis, theta, and also the classification. It means that connects is just ellipse. For example, this is also ellipse. For example, the hyperbole. You see center, axis, and on the end you can see it's hyperbola. Okay, so you have just few yeah, yeah. And now just let me show. This is no, this is not. No, this is also not. This is our paper, and let me very shortly explain how it works. In the bot periodicity, it's mean that it's possible to realize any Clifford algebra as a matrices, some smaller Clifford algebra, especially if we have a geometric algebra of conics, which is signature 5 3. It can be realized as a matrices times 2 times over matrices times 2 times over CL31, or as a matrices 4 times 4 over CL31. So this is why the any object is represented as a matrix 4 times 4, because such that the element of this matrix are elements of compass rule algebra. For example, it's better to see in text file. It looks, for example, like this. So, and typically on the diagonal we have some CI compass rule element, and there are some numbers somewhere else. For example, we compute the wedge of this, for example, and maybe there are some examples. For example, the point looks like this. This is the typical GAC point, and this point is represented by this matrix. So we have this element which belongs to CRA, and then these two extra number are coded in the upper part of matrix. And this is the point, And for example, this is ACA. Yeah, this is, they have been published, I think, one year ago. I can send it to you. Okay, this is so. So in our settings, any element of the geometric algebra of conics is represented by matrix 4 times 4, such that the elements of this matrix belongs to compact structural algebra. So, and okay. So it was the next what I wanted to show. Then the fitting. We received from Paco some real data for the signal, and the for example, it's some set, and in this is set which is balanced, and we use CGA to find the plane, which is the plane where the signal lives. And if we have a just balanced signal, we have a circle in the space, and then there is just one plane which goes through the circle, and there is just one sphere which goes the circle. It's nothing special. And then we have the plane where all the data belongs. Then we can rotate this plane to XY plane, and then we can fit them by ellipses. And now this is the result. It's a circle because it's the first example the data are balanced. But if we have something more complicated, some unbalanced system, for example this, we have two circles which are in the space, and now if our techniques is always to fit all this point by the plane and the sphere. I use these two objects to separate the points from these two ellipses. So now you can see the plane is not exactly fit. It's not exactly fit this the main cloud of the points, because the second cloud a bit of change the rotation of the plane. So, but it's not a big problem, because it's significantly closer to the plane, and also the sphere which is exactly between, which can be also used to separate these two sets. And now you can see we separate them, and you can see these two planes. These planes belongs this data, and these planes belong this data. And now you can see these two objects. This is the part which is balanced, and it's a circle. This is why you are not see this circle inside and outside, because it's circle itself. And now this is the error. So we are able by these techniques found the set of points which are not balanced, and find the ellipses which is fitted by these points. And I have two more. I have two more examples. It works also for the strange. For me, maybe it's not so strange of the points, but still, if we are find a plane, we can project these points to the plane and find the ellipse, and it can mean something. And yeah, yeah, it should be. And yeah, in this direction, it's challenging what's happened if these ellipses are 3 or 4, because I we just analyzed the situation where we have we have just the balance signal and unbalanced part. So we have always the circle and we have always the ellipses, which is inside or outside the circle. So by finding the plane and the sphere, we are able to separate these two cluster of the points. But in the case of the three ellipses, it has to it needs more to think about it, and it's and yeah and yeah it's yeah yeah you can see in this in repository all these examples. The uh, there are some procedure like fitting points by plane, fitting points by sphere, and everything is set here. This is the test. You will choose how what is the maximal distance of points from the plane, and now you can see which points are close to planes and which points are not. So this is the next what I would like to say, and the last one, it's a following. It's yeah. The last one is the following. If we have a if we in the paper, how I said, every element is is represented by matrix 4 times 4. And if you see this matrix, then this is maybe, I think it's some ellipses, exactly this. If we see this matrix, you have always on the diagonal, you have some compass rule algebra element, and then you have some numbers. In fact, in the case of ellipse, you have on the diagonal sphere. So in this case, you have some sphere which belongs to ellipse itself, but but this sphere is not sphere inside or sphere outside. And I did some experiments with the signal, and if you see these examples, then uh, this is some errors, and maybe maybe this is better. And uh, I think, which one is this? I think the blue, this is three ellipses, three different ellipses, and the black one is a circle outside, and the blue one is a circle inside, and the red one is a circle on a diagonal of the matrix. And you have the three examples. And I think what can be challenging is if we will describe we would like to describe the transformation between two ellipses, because my idea is that if you have some signal, you have the set of ellipses in the space, and if you take the one ellipse and second ellipse, maybe they are same, but maybe they are not exactly the same. It's not ellipses. I think on the start you have the circle, and then you have the circle, but the error has to appear in some time. So now, if you have a circle and then you have the almost the circle, you will find the first non-trivial transformation, and then you will be more ellipse than circle, and the transformation will be continue in the some way. And I think it can be interesting to try to found, because if something will happen, it maybe some error will happen. Maybe the error can be some conformal transformation. I don't know, maybe not. But if the error will be some conformal transformation, it's possible to recognize which one it is on the start. So there is Leodor's nice paper where all these transformations are classified, and in CGA it's possible to classify bivectors to six classes. And for example, this is origin and vector, which is TC is a translation to some point C. So there are 6 types of vectors, and some of them commute and some of them not. And if you see table, there are these six types of bivectors, and some of them not commute and some of them commute. If they are commute, the motion is very easy to describe. For example, if we have a direction vector, it means translation, and do line, which means rotation, you will receive exactly cylinder motion is mean screw motion. So any conformal transformation are completely described in a very nice way. So they are completely described in a very nice way, and we are interested about some signal which can, I don't know, maybe the transformation is not conformal, but maybe it is. And so my idea is to try to analyze the signal in this way. We have the circles, which are circles, and the circles starting to be ellipses, and between any 2p we have a one circle, second circle, next circle, and we have always some transformation which can be identity, which can be against identity, and now something happened, and it means that something happened. So it's like a rotation. If something start to rotate, it will be rotate in this direction again. So to find this error in the time where the error start. So, and it's complicated to describe the ellipsis transformation, but in the case of ellipses, we have a circle inside and circle outside, and also we have this circle which is not sure what it means. So we have in fact 3 circles. 2 of them are from the definition of ellipse, and this one is from the representation of the ellipse with some special algebra. So we have free conformal objects. So we have a free conformal transformation. So we have a free bivectors, which are logarithms of these transformations. So we have a free possible conformal motions, and we can analyze what it means in particular signal. Okay. Yeah, that's it. Yeah, it is. Thank you.
I have some comments, observations, and questions. So, yeah. First of all, I suppose the motivation of this new representation using compass rule algebra, try to put the matrices. I think it's motivated because of the complexity of the conic geometric algebra, right?
The motivation of this implementation in matrices is how to implement any algebra in software which is available now.
Okay.
If we have a Clifford packages where the conformal geometric algebra and compass rule algebra works well, for example, also in Sugar, in MATLAB, conformal and compass work well, and we would like to work with higher algebras, and geometric algebra conics is typical example, then we don't need to set the different signature. We just set the right size of matrices,
Okay.
and MATLAB works with matrices very well.
So in the end, we will have something much more efficient
Yeah,
because of the system. Yeah.
It really works very fast.
Very good idea. Regarding your last your last figure, I think that prediction with CGA or compass rule algebra are very interesting because the idea of detecting what is telling us the curve, which is a power quality problem in a power system, is very important to be detected in the very beginning. So in power system, we have two main focus. We focus on frequency domain or we focus on time domain. When we focus on time domain, we get every instant we get a sample of the measurement device, we get a point. And we need to wait for the whole period, which is a lot of measurements depending on the sampling frequency, to get the idea of the shape. It's an ellipse, it's a circle. So if we need to wait for a whole period, then we are in the frequency domain. We need to wait for a period, we need to perform the Fourier transformation, and we need to wait at least for 20 milliseconds, which is so much. So right now, the techniques that power system engineers are expecting are those who can deal with points, with samples coming from the measurement device and trying to predict the error, what you call the error. And this is one of the main applications, because right now we have some methods to detect the disturbances in the power system, the power quality problems. Yes, waiting 20 milliseconds is okay. We can detect some of them, but we need faster methods. We need to predict in somehow based on the circles or on the change or in the error.
But in fact, I need just 5 points.
Yeah.
I don't need to wait all the circle.
Yeah.
I need just 5 points, and then I fit it, and I have a prediction all the signal.
So it's a very good approach, because you need, the minimum amount of points. The problem then is, the noise, because they are together. You have some noise, you will get very different shapes. So, but the idea is very good. So I like so much. So thank you so much. I don't know if there are any other questions.
We have.
Thanks. How does the fitting procedure work mathematically? Do you always get an ellipse from 5 points?
No, of course not. The first example give us the hyperbolid from the 5 points.
Right.
It works. It's based on the last square method, where the distance is a distance which is called.
I think he is asking about the 5 points fitting. No, or
I'm just interested in the way you implement. Is there a simple method for fitting? I guess a 5 blade to 5 points in this conformal geometric algebra. How is that fitting performed?
No, it's in conformal geometric algebra you can.
If you take 5 points, you can wedge them together. I assume it's like CGA, and then you get the exact conic through those points. But if you have an over-specified problem, how do you implement the least squares?
No, it's just algorithm. I can go in detail, but it's just you have it's very similar to last square method. You are looking for the function in some shape, and you have a lot of points, and you compute some distances, and then minimize some function and looking for eigenvalues.
Okay,
and
so you get a.
It's
by scalar product of
yeah.
point with the unknown.
Yeah. and it's
So you have a traditional minimization problem.
yeah,
then.
it is traditional minimization
Right.
problem, and it's
function, but with respect to the geometric product.
it's the function you are the function you are minimized, the distance you are minimized between point is based on the scalar product which is in geometric algebra itself.
Which is automatically invariant.
But you need a microphone, please. If you want to tell something, because
I'm close to it.
Right. Cool.
that's all.
I think it's not the interesting thing about it. It's that the if I say the classical algorithm is adapted in geometric algebra. So after this procedure, you will exactly receive the volume for the element, and you will receive exactly the conics you are looking for. So yeah.
And oh, can you yeah, can you say something for Santiago? Santiago is raising the hand.
Santiago, are you? Can you hear us?
Hello. Yeah, I hear you.
Oh.
You hear me?
Yeah.
Yes, yes.
Mm. Yeah, I have a question. E- Can I do it, or you want to go first?
I think five more
Okay.
minutes.
Just well, Jaroslav, thank you for showing us this. My idea is, let's see. You compute the circles and this error, like the shifting. How fast is this computation? Can you do this? Like, have you measured? Well, this is a Python tool, yeah. Then how fast are you computing this? And if, for example, can we like see it like in a transient form, like we just can see how it shifts from one circle to the other position, if I understood well. It's a like a dynamic visualization. I mean,
It's a it's something we would like to do. We don't have it. It's just the idea, because the idea is it's complicated to describe transformation between ellipse and ellipse. It's some kind of elliptic transformation. I don't know. Maybe I think it's very well known, but I don't know how it works. But we have a CGA compact. We have a CGA, and in CGA, if I have a, in fact, we have two CRA. We have compact rural algebra, and if I have two circles, just multiply them. I will receive the transformation between them after some normalization. So in this conformal 2D, 3D algebras, it's very easy to find the transformation between the objects. And after I will, yeah, yes.
I think we should, yeah, maybe take a call, and I might be interested on, yeah, on this
Yeah.
visualization, the 3D
Yeah.
visualization. So, yeah, very good. Thank you. Yeah.
Do with the robots that I have two circles, I will find a transformation between them, and I will compute the logarithms of this transformation, divide by 10, and then I will receive the transformation, which is just one part, and then I will apply it 10 times, and I will receive the visualization of the conformal motion.
Okay, thank you, Santiago. I think we have 2 more minutes for a question for Sayuanju. So can you ask, please? Sayuanju, are you there? He raised the hand.
Maybe later.
I don't know. Later.
I'm able to answer.
Okay,
anytime.
so thank you so much, Jaroslav. So our next presenter is Mr. Ahmad H from Port Said University. Oh, he was there. Yes. Oh, sorry, we cannot hear you, but I don't know what's happening. But we are a bit late. We need to move to the next presenter. Maybe you can ask. Maybe you can ask later. Yeah. So or put the question on the chat if you want. So our next presenter is Mr. Ahmad H, which is a creator of the Geometric Algebra Fulcrum library. Okay, Mr. Ahmad, the floor is yours. So I think you need to turn on your microphone. Okay, thank you.
Hello, everyone.
Hello.
Is my voice clear?
Yes.
Okay, glad to be with you today and very happy to present my work in front of this great panel. I'm currently sharing the screen. Can you see the slides?
Yet?
Sorry, the connection is went out. Can you see it now? Okay. I will try to share again. How about now? A bit. Okay. Oh. Okay, I will try again. Sorry. Okay, thank you. Sorry. Okay, I'm going to talk about the design of the Geometric Algebra Fulcrum library, mainly about the collected lessons from coding a geometric algebra on a computer. My summary is simple, what GA-FuL is and a brief history. And the main part is the lessons from other libraries and personal experience. I will talk briefly about its design and use cases and future developments. The geometric algebra fulcrum library is, if you go to the main repo, you will find some description, a unified generic extensible C# library for geometric algebra, geometric modeling. It can and an API is used to make it performant in several scenarios and can be used in several use cases. In the paper we wrote last summer, Paco and I, we have many details about the library. If you want to go to it, I will not talk about every detail, of course, for the time, but I am going now to talk about why I created it and how I arrived at the current design. The first time I knew about geometric algebra was in 2023. I immediately saw its potential and importance. I started thinking how a good software implementation should be like. I'm a software engineer. I know a bit of mathematics for my work in computer science and computer engineering, but I had to learn a lot, and it took quite a lot of time to learn properly. I had to start implementation from the algebra itself, not from the applications. I had to know how to represent a multivector in computer, how to implement basic algebraic operations, how to code algorithms based on geometric algebra, and how other libraries did it. Of course, a lot of work is done in this area back then, and it was many challenges for all people. I immediately realized because of the size of a multivector in a high-dimensional space, it's hard to implement efficiently. It will be slow. I decided to create a small GA to code compiler. I called it GMAC back then. I wanted to avoid to have to use a full representation for multivectors because my main focus was on the performance. I created a proof of concept during my PhD in 2010, and I restarted developing GMAC from scratch during 10 years from 2011 to 2021. Of course, I have several papers to describe the development, and GMAC is quite fast in its produced code, but it has limited scope. It worked well for low-dimensional geometric algebras, but I selected to use a specialized domain-specific language for describing my geometric algebra algorithms. I call them macros because they are not full algorithms. You can't create for loops. You can't create if conditions inside the DSL itself. I didn't want to go into a full compiler implementation. It would take a lot of time and deviate me from the learning and the efficiency computation. I relied on the user being a software engineer himself. He just wanted a critical section in the code to be performant. So he should use GMAC for implementing this section, a geometric computing section using geometric algebra, and put the section as he likes into the main body of the code. GMAC produced very efficient code indeed, but it was hard to use for most people. The domain-specific language was difficult to extend and debug. Adding new features to it, I'm essentially working with a compiler, a source-to-source compiler, so it's difficult to modify. There was no visualization capabilities possible back then. And of course, rapid prototyping requires fast feedback from the computer. This wasn't possible with GMAC, and the practical use cases were a bit limited for it. A successful use case for it, before I talk about it, this is an example of GMAC. You write some code like this on the left. This is the DSL of GMAC, and it goes through the compiler and an optimized code for C# in this case, or any other language you need, would go from the other side. One use case I worked on, and it was very successful. We had a grant in 2018 to create a simulator for representing electromagnetic wave propagations for high frequency, and to see how the wave or the transmitter would affect the environment around it in terms of signal strength and power and these things. As part of the project, I had to create a geometric algorithm for finding the reflections of rays on several surfaces, as the figure on the left. The ray would bounce off surfaces in 2 dimensions and 3 dimensions. 2 scenarios are used typically in this domain. And I had to find the region in which a point resides in space in relative to a signal source and a reflecting surface. This algorithm is very simple, but the main point here is when using geometric algebra, I managed to unify the 2-dimensional and 3-dimensional cases using very similar formulations. Very few modifications had to be made. And the resulting code due to GMAC was very efficient compared to even the commercial packages on simple scenarios, of course. I used the homogeneous geometric algebra formulation. It's very basic. If we look at the middle column in the table on the right, the formulation is very close in 2-dimensional and 3-dimensional cases. The vector algebra formulation is quite different. It's ad hoc. The expressions are a bit difficult to follow. It can be generalized to other dimensions. If you want to generalize to this problem for some reason to higher dimensions, it's straightforward in geometric algebra, not in vector algebra. And the performance we got was very beautiful compared to other packages. Here we say a two-dimensional scenario and the propagation colored in red for high energy points and other colors in low energy points. And also a 3D-dimensional scenario is possible using the same algorithm. The speed up, of course, is below, and it's a big speed up from 3 times to 10 times or more. In 2019, Baco contacted me. To help him with the geometric algebra modeling of electrical power systems. He provided me with many use cases and how an interested user should use a software to develop geometric algebra algorithms. I started gradually adding more ad hoc features to GMAC. It wasn't designed to handle these features. So gradually I gathered a lot of lessons and experience during this time to create a new library that will be very useful in the future for other people and other use cases. Okay, I'm now going to talk about the lessons. This is the main part. This is not really present in the paper, so I wanted to focus on it because it might be useful for other developers for geometric algebra packages. The first lesson, of course, anyone working in computational modeling already knows about this. Real numbers are not computationally real. We can't arrive at a real number to arrive at an arbitrary real number unless we use some kind of process. For example, counting, we can go from 0 to 1 to 2. This is a process. Addition and subtraction is an algorithm to skip counting and go forward and backward on the natural number points. Rational numbers through division. This is another process. We need to simplify the numerator and denominator to arrive at the simplest form for a rational number to be able to compute with it. Real algebraic numbers arise from solving equations. Arbitrary real numbers are very different in their nature. Arriving at the number e requires processes, mathematical processes different from pi. And in a computer, we can't arrive at an arbitrary real number in arbitrary time and arbitrary memory. We can't restrict all of them at once. Either we can use a generic representation, for example, a symbolic expression, a rational number representation, or an arbitrary precision floating point, but this requires unspecified memory and unspecified time. Or we can fix the size of the representation, like the floating point numbers in the IEEE 754 standard. In this way, we can't arrive at arbitrary real numbers, but we can only approximate them. And so they are not accurate enough for some applications. I found that computational use cases for numbers are vary considerably, but the algebra rules are the same. Even in ordinary algebra, complex algebra, quaternions, matrix algebra, the algebra rules are the same. We only need to change the scalar representation and how to avoid the errors. The strategic solution to this, in my opinion, was to make an algebra implementation agnostic to the specifics of scalar representations. The second lesson, of course, we all know about it. The high dimensionality of geometric algebras result in very high dimensions in the k-vectors and the multi-vectors we need. So if we need say a 100-dimensional geometric algebra, some applications may require that, especially in signal processing, or even a 15-dimensional geometric algebra. It might be out of control in processing time and memory. It will not be feasible at all. So we have to use some kind of simplifying assumptions. The one I'm using currently is that I will address more. Either low dimensional geometric algebras, not more than 10, or sparse multivectors in arbitrary dimensional geometric algebra. So I have to use efficient data structures and algorithms for storing and processing sparse multivectors, and use metaprogramming or code generation to produce an efficient implementations on these geometric algebras. The third lesson I learned is to prepare for multiple algebras. There is a huge body of knowledge in computational modeling relying on other kinds of algebra, complex and quaternions and matrices and others. It's not feasible to start from scratch and forcefully impose geometric algebra to replace all other algebras. At least not right now. It will not be accepted simply. And it will be isolating. So interfacing with existing non-GA libraries, especially the ones based on matrix computations, is computationally mandatory, for now at least. It should be made easy to interface with these libraries. Practically searching for a single geometric algebra to replace all other geometrical algebra is too extreme for the moment being. It might be beautiful mathematically, but from a practical point of view, it will alienate a bit our efforts to spread the word for geometric algebra. So I decided to prepare my software to easily handle multiple geometric algebras at once without no hassle. You can use multiple geometric algebras in your problem, in a single problem, without switching overhead or whatever, and to also incorporate other algebraic systems in the processing if you need. If you are familiar with complex algebra and it solves your problem, okay, it's no problem. I can add a bit with my geometric algebra knowledge, and we can work collaboratively without any hassle. And gradually, I can show you how to incorporate complex algebra into geometric algebra, and we can go on from there. The fourth lesson is to build a complete system. GMAC was a partial system, a code generator, but I needed a complete system, a complete from a human side of view. If you look at this symbol diagram, I identified 5 stages for interacting with a computer in a typical geometric modeling scenario. The human side, we are very good at imagining geometry and expressing ourselves in the symbolic language of algebra. Computers are not good at this unless we use some form of artificial intelligence, and even at this level, and of course computer algebra systems, even at this level, we are in the driver's seat, not the computer. So it's mainly a human endeavor at this side. On the other side, when we go to algorithms and computer code, this is more suitable for machines. Specialized people work on this to make algorithms general and efficient, and the coders or software developers also have a gap between an algorithm and the computer code to make it suitable for the hardware. For example, a computer code written for the CPU is very different from the same code written for a GPU. The algorithm might be the same or very similar, but the code is very different depending on the machine or the hardware architecture we are using. The important factor here is the feedback loop through visualization. A computer code, if I need to be useful, especially for prototyping, for rapid prototyping, we need a visualization capability. For example, through a graphics engine or a physics simulator to display visual images to feedback to the human side again through the visual system. This is a complete system that we can see in most of the successful packages. Things like MATLAB, Mathematica, Python, Julia, they all implement this cycle in one way or the other, either through the user interface, like in Mathematica, for example, or through code like Python, Julia, and MATLAB, or add-ons or libraries. Geometric algebra is unifying, powerful, and versatile. Any software based on GA should be equally generic and powerful. It should implement the full cycle for full human interaction. My strategic solution, we need to do the same holistic approach for geometric algebra-based software development. The fifth lesson is to rely on data, data-oriented programming, not object-oriented programming. The engineering method requires data. Without data, there is nothing. We start to find the patterns in the data, express them geometrically, and then through algebraic expressions, hopefully through the geometric algebra. Then we evaluate and code and go into several iterations until we perfect the problem solution. The software architecture should reflect this process. We should be targeting or facilitating the data flow inside the software itself. Object-oriented programming has many problems in this regard, especially when you create a complex hierarchy of classes and objects. It will be very difficult to extend and scale, and it will be very difficult to maintain. Anyone who worked with database systems knows this. You also always need something in between your object-oriented code and your database, because a database is focuses on data first. We need this conversion back and forth between them. But if you already have an architecture that is based on data-oriented programming, you will be solving much of the problems you will face during your development. Data-oriented programming has four simple principles. The first one is simply to separate the behavior code from the data. I create a multi-vector, for example, a class to represent multi-vectors, and I put the geometric product code inside another class. This is a very simple approach. Not include the processing code inside the class itself that holds the data. This simplifies the design a lot. Also, the second principle is representing data with generic data structures. This goes very well with my the need for using scalars that are generic with geometric algebra. Don't use specific data types. Try to use template metaprogramming or generic templates for your code, and so it's general at most cases. The third principle is to make data immutable. I typically represent my data structures that hold the scalar elements in a complex number or a vector or a multi-vector in a small data structure. Then I will not prevent, after creating this data structure properly, I will prevent the user from modifying it. If he needs a modification, he will need to create another one, another version of the modified data. This is very good when handling data streams. If you have a complete signal, for example, you need to pass it through some kind of block to convert it to another signal, say filter it or whatever. The input signal is different from the output signal. It makes very sense in code to make the same approach, not modify the signal itself in memory, but create another version from it. The last one is separating data representation from data schema. It simply says we use interfaces to define the contract between the data and the operations we perform on the data. We might have in our library several objects that might be used as vectors. For example, a two-dimensional angle, a simple angle can be regarded as a vector, but a rotated vector by this angle. So it can be used sometimes as a two-dimensional vector or as a simple angle to have the cosine and sine object handles or implements the interface describing vectors and the other interface describing angles. And of course, we have a fallback object that a generic vector, and we have a vector for the multi-vector space, and so on. So we can have multiple representations that perform the same operations using the contract we call the data schema. The last lesson is to adopt successful designs. We shouldn't think from scratch every time. I will talk here about two scenarios, but it's a more general principle than that. For example, numerical linear algebra aims to solve problems of continuous mathematics using finite precision computers. Numerical linear algebra applications are very vast, and we all use it every day in all in social sciences, not only in engineering and science. So it's described as fundamental to the mathematical sciences as calculus and differential equations, even though it's a comparatively small and maybe somehow new field, only 50 years in development. NLA uses properties of vectors and matrices to develop computer algorithms that minimize the error introduced by the computer, and also concerned with ensuring that the algorithm is efficient and feasible. Common problems in numerical linear algebra include, of course, decompositions, factorizations, eigen decomposition, and it can be used to solve linear equations and locating eigenvalues and least squares optimization. Most of the literature in geometric algebra I am currently seeing uses linear algebra to implement such algorithms. Curve fitting, like the beautiful example of the ellipse fitting, it mainly relies on matrices at a later stage after the development of the geometric algebra algorithm. It would be very nice if we could develop numerical geometric algebra algorithm directly to mimic some successful libraries in numerical linear algebra, so, things like Labac and the plus library and its number needing linear algebra daily. If we could make a leap in geometric algebra development to follow this success story and develop numerically based libraries for numerical geometric algebra, it would be a great step towards its adaptation. The second scenario is to use application programming interfaces instead of domain-specific languages. This is important because domain-specific languages have many problems. It's essentially creating a compiler, but an application programming interface is simpler to create and extend and to handle our computational needs. Most successful packages for geometric modeling, like for example 3D Max, AutoCAD, or other game engines like Unity and Unreal Engine, rely on APIs mostly, not domain-specific languages. So we should follow these success stories in our development for an interface for geometric algebra. Relying on APIs is better in my experience than a DSL. Now for the final part about GA-FuL itself. Most of the details are in the paper, of course, but I'm going to talk here briefly. I wanted to find a way to convert my algorithm into code in high or low dimensional geometric algebras, but using sparse vectors. I wanted to be able to perform a complete cycle in the software for prototyping, including the visual side, and I wanted to use whatever kind of scalars representation I needed, floating point, rational, symbolic, whatever. So I decided to make a 3-in-1 code base for all 3 scenarios that relies on numerical prototyping, a generic API, and the meta-programming code generation capabilities. I had 5 design intentions in my design: to separate geometric algebra operations from the scalar representation, to reduce memory for sparse multivectors, and have meta-programming capabilities, a nice layered system for a wide spectrum of uses and ease of use, and a unified and generic extensible API for several classes of applications. Of course, this design should follow all the data-oriented programming principles I talked about earlier. There are 3 main layers in geometric algebra program library. The algebra layer is the lowest one. Representation contains some classes to represent the data inside a multivector or a vector or a matrix. and the processors are specialized components that hold the processing code for all these objects and how to convert between them. This algebra layer is the lowest layer in the system, and everything else relies on it. The modeling layer contains a geometry, some geometry components for describing, say, 5-dimensional CGA or BGA geometry, not the algebra itself, but the geometry that builds on it, how to represent lines, planes, and spheres, how to intersect them, how to visualize everything, and in the future, how to make geometric calculus computations on them. The metaprogramming layer uses the previous layers to implement the code generation in the best way possible for a good software engineering. This layer is typically used by the production code team, not the investigation team. I assume there is a need for fast performing code, so we need this layer for a good software engineer to produce from the final model the desired code. Of course, we have some utilities, and we can interact with external packages like symbolic and numeric packages, graphics packages, signal processing packages, and we can make many applications using this layered architecture. Metaprogramming GA-FuL, if programming is like creating a robot to do some tasks, metaprogramming is like creating a robotic production line for creating robots. So metaprogramming allows programs to treat other programs as data by reading, generating, analyzing, and transforming or modifying other software, or even themselves at runtime. This is a general definition of metaprogramming. It has many benefits like keeping code small, simple, not repeated, lightweight, intuitive, and scalable. And there are many techniques for metaprogramming. I'm choosing the abstract syntax tree manipulation technique for my work in GA-FuL. I'm creating a symbol from the algebraic expressions automatically inside the memory, a simple abstract syntax tree for how to compute this expression using the algebra of choice, or even multiple algebras. It's not a problem. There is no overhead in converging between them in this stage. And then I transform this expression tree into the basic scalar components of the algebra. For example, in complex algebra, the real part and the imaginary part are two real numbers. A multivector contains 2 to the power n scalar components, whatever. Then I try to optimize the scalar computations and produce the final code using a selected target programming language. I'm using metaprogramming in GA-FuL to make many things. For example, of course, generic optimized code, generating visualization code using external packages like GraphViz and Babylon.js and bootGAC for ray tracing, and generating structured latex code for reporting and technical or academic writing. I have used the library successfully for all these scenarios without problems. This is an example of a visualization using bootGAC. It's a ray tracing visualization, a sequence of images to show the family of rotations between two vectors. This is a recent development. I can also generate for Babylon.js and GraphViz. And some use cases of finally some use cases of the library. You can read more about them in the papers. For example, the resection problem in geodesy. We managed to test several algorithms in geometric algebra, and we had very good performance when applying the metaprogramming capabilities of GA-FuL, and got even better than the best handwritten optimized algorithm in the literature. Another one is the geometric generalization of electrical frequency concept using space curves. We also produced many symbolic expressions using GA-FuL in this context. We made some very good visualizations. The ellipse fitting of space curves, we had some good work done, and I used the GA-FuL for investigating and plotting the curves. The final implementation I used was in MATLAB, but the investigation was done in GA-FuL. And of course, this gave me a very beautiful use case to develop my library furthermore. The final one is generating a full MATLAB toolbox for low-dimensional geometric algebras. This was just a fun project, but it is practically usable. I used the metaprogramming capabilities not just to produce a single algorithm, but a full library for all the main operations of geometric algebra for n less than or equal to 9. And the paper and the repo contains some samples on this MATLAB toolbox. Finally, the future developments, I want to incorporate geometric calculus in the mix and generate geometric algebra libraries for Python, JavaScript, and Julia because they are very important computationally for many people. Implement interactive visualizations in JavaScript and Babylon.js. This will attract more people to the subject, of course. If I could add Coda and shader languages as targets for metaprogramming for my library, it will be great to make even better performing implementations. Of course, developing and implementing numerical geometric algebra algorithms, this will require the efforts of many researchers, of course, but I'm dreaming about reaching this level in the near future. If we could integrate with artificial intelligence and meta-heuristic optimization systems, so the geometric algebra would be the constraints on the system, and we let the AI and the optimization devise new designs and new solutions that even we can't think about or imagine geometrically. It would be great, and this would be explainable AI in some way because it relies on geometric constraints. Of course, collaborative research in geometric modeling. This will give me more use cases to develop the library and make a lot of educational videos and blogs, blog posts about all of it. Thank you. I hope you enjoyed this talk.
Thank you very much, Mr. Ahmad, for your nice presentations. Incredible. I thank you so much for it. So it's time for question or comments.
I have a question. I already wrote it in the chat, so I can read it maybe easier. My question is to Svea, what made you so interested in and convinced of the potential of geometric algebra 22 years ago in 2003? Because there you started, and you have a long history now. But what was the initial thing that got your interest?
I'm an engineer. I studied mechanics. I studied in my preparatory year. I had a question about the complexity of the expressions. I couldn't understand many of geometric concepts behind what I'm being taught. I felt even my professors didn't understand it that well, especially when you mix translational motion with rotational motion in physics, in geometry, in engineering. It's very complicated. I was frustrated. I am a good coder. I have a good mind, I believe. So why didn't I understand all this? Why didn't, and my colleagues, the same problem. It stemmed from an educational interest. I want to be a good doctor, a good professor. I want to explain this to my students. This is the main motivation even until now. For educational purposes, geometric algebra is perfect. Even if it's not yet very efficient in all the production code, and I'm trying to solve this problem with my library, but I managed to go cross disciplines using geometric algebra. I understood frequency propagation, although it's not my main interest. I understood electrical engineering. I understood mechanical engineering. This is all because of a simple language that connects all these fields together. Of course, inside the same field, you can connect many techniques using the simple geometric intuition. It's great. It's a great tool for thinking.
Thank you for your answer. Thank you.
Thank you.
Any questions? Okay, a question from Joseph Wilson.
Hello, thanks for that.
Hello.
I'm interested in the metaprogramming layer that you have for GA-FuL. So you have a routine or something where you represent operations symbolically and then simplify them. Say, for example, if you're applying a rotor to a vector, the result has some terms that cancel.
Yes.
What do you use to symbolically reduce the expressions? Do you use a computer algebra system, or do you use some rules that you've handwritten? I'm doing the same thing with the Julia package at the moment, and I'm wondering how you are doing it yourself.
Of course, the full code repo online contains the full implementation, so you can go inside and read every detail you need. But I will give you a brief summary. I need to use a computer algebra package. I'm currently using two, Mathematica, Wolfram Mathematica, and if you don't have it, there is a built-in computer algebra package inside the .NET framework. It's less powerful, but it works. The main idea here is to convert the geometric algebra expressions into a series of assignments on scalar values. Then you simplify each scalar value individually, as if it's a separate expression. This is where we use the computer algebra system. But after that, I used classical compiler optimization techniques, data flow diagrams, elimination of constants, propagation of constants, elimination of common sub-expressions. This is all standard compiler design techniques that I already know from my study as a software engineer. You can, of course, find it in any compiler design software and select the techniques you need to produce the best result for your domain. This is the summary of the whole process.
I suppose, in my experience, I used an external computer algebra package at first, and then I realized after a while that you don't actually need many complicated features from a CAS to simplify most of the expressions that you produce when you're stitching together geometric algebra products. You just need basically a way to form polynomials and factor them and reduce terms in a very, very simple way. And so I'm trying to build a very, very simple computer algebra system that's not big, that just does just enough to reduce expressions. But it's interesting to hear that you use Mathematica as a kind of API. Do you still do that, or have you?
Yes.
Right. Do you think that it's necessary to use a fully blown computer algebra system to simplify the code?
No, it's not necessary, but for me it was important because I already know Mathematica. I wanted to not to waste time learning another package, but you can use anything. The architecture is extensible. You can use any plugin, any other symbolic simplification computer algebra system. But I'm using Mathematica for another purpose. My library also can be used for symbolic investigations, not only for efficient code generation. So I need a powerful backend. Mathematica is very good at this. Many of the expressions we wrote in our papers, I arrived with not with a paper and pen, but with the use of GA-FuL with Mathematica. So in my use cases, I need it for a full investigation of symbolic expressions.
Thank you.
Thank you.
I have one last comment or question. In the abstract in your paper, you say something cheeky, that the metaprogramming code optimization capabilities of GA-FuL are found to be unique among other systems. Which ideas do you think are unique? Curious, because I want to steal them.
Well, the core compiler. In the previous design in GMAC, it was a typical design. You create a DSL, and of course, there are good people working on the same idea right now in GAALOP, for example. It's a good idea, but for my purposes, I found it a bit limiting. When you create a DSL, it compiles using a source-to-source compiler. This is not unique in the field of computer science, of course, but I'm talking about uniqueness in the field of geometric algebra implementations. All the ideas are typically found in computer science, nothing new. But using them for geometric algebra, I found it to be very necessary to produce efficient code. There is no way you can find a generic library for generic geometric algebra implementations that can be used for production code in time-critical applications. You have to find a way to translate the expressions into machine code that is very efficient. This is only done in my case through the handling of an abstract syntax tree. The handling process itself relies on a generic implementation. I'm not creating a specialized code to translate from the geometric algebra expressions and handle the geometric product, for example, separately from the code that handles the geometric product for numerical values or from symbolic values. It's the same code. I only added some optimizations into the abstract syntax tree after the creation of the abstract syntax tree. The uniqueness here is in regard to the simplification of the whole system, not to create specialized code for the numerical processing separate for code for the optimized code generation or from the symbolic manipulation code. It's all the same code in the geometric algebra side.
Yeah. Thank you.
Thank you.
Thank you so much, Ahmad. I think we have some time later on, or maybe we can discuss by chat or by email. So
Okay.
thank you again, and the next time. Our next presenter is Dietmar Hildenbrand, to talk us about GALOP. So the floor is yours.
Yeah. Okay. Okay, can everybody hear me?
Yes.
Can yeah,
Yes.
you're for sure. You're
Yes.
for sure.
Yes, yes, we hear you.
Okay, okay, fine. So welcome everybody to my talk about GAALOP. I decided to start with an example for computing with GAALOP, dealing with the beach, because you mentioned yesterday that the beach is so close to your university and they do not accept um, that you get a real beach with sand and so on. But I have two different experiences. So for instance, sometimes when I was in vacation in the Netherlands, this is a picture. I was motivated to think about how can I compute the horizon that I see. And I would like to use this example then. Because I think it is a small example, but can show the performance which is possible with, or give a feeling of the performance which is possible with GAALOP. Okay, I will talk about this example, as I just mentioned, then give you an overview about the architecture of GAALOP. We'll shortly discuss a new solution for FPGAs. It is a brand new solution because I yesterday discussed with Santiago, and it was a nice experience to hear how he is working, and I was thinking about how can we combine that. Then our tool GAALOP is also available online, called GAALOP Web. I will present this and give some examples. Okay, that's what everybody know. Just a short recap for people not so much knowing conformal geometric algebra. We have 5 basis vectors, E1, E2, E3 for the 3 spatial coordinates, and then 2 additional ones, E0 and E infinity for origin and infinity. We have 2 to the power of 5 means 32 basis elements, scalars, vectors, bivectors, and so on. And most of the expression have a geometric meaning. So vectors, for instance, have the meaning of spheres, planes, points. Bivectors, the meaning of circles, lines, and for instance, these basis elements in principle are the complex numbers of quaternions. A sphere can be expressed as center point minus half radius square E infinity, and the plane can be expressed simply as n plus d times E infinity, where n is the normal vector and d is the distance to the origin. Intersections can be expressed very easy. If you have A, B as spheres, A square B describes the intersection of the spheres and represents a circle. And the nice thing in geometric algebra is that you do not have any special cases. So also the sphere and the line can intersect simply with a wedge product. And the result in this case is a point pair as intersection of sphere and line. Circle can be expressed in a dual form as the outer product of 3 points, and the line can be expressed if the third point is simply E infinity. Rotor quaternions can be expressed very, very easily. The inner product of vectors is the same as the well-known scalar product, and additionally, if A and B are 2 lines, 2 planes, 2 circles, in principle it is describing the angle between the cosine of the angle between them. If A and B are 2 points, in principle the distance of the 2 points is described. If A and B are point and plane, the distance also between point and plane is described. And in the case of the inner product of a point and a sphere, this is described mainly by this tangential line segment. Here, this is the expression a square, this distance square is the same as minus 2 times inner product of sphere and point. And this is what we in a minute will need for our short example. Oops. Okay. Okay, so as I mentioned, I would like to describe the horizon as a geometric object. The horizon, which in principle is a circle. How can I compute that if I know that I'm standing at the beach and this is my eye point, and I additionally have the Earth described as a sphere? How can I simply compute this horizon? Means I have P and S, my eye point and the sphere, and what I need is my circle describing the horizon as C. So the first question in this example is, which sphere intersects with the sphere S at the horizon circle? I think it is clear. So, pardon?
You are asking?
Yeah, yes, I'm asking.
Yeah, P is the center and the tangent lines.
Yes, yes, exactly. Why do you say there are many? Yeah, yeah, sure. P is the center, and okay, and what is the radius of this new sphere K? We already saw it. Means the radius is simply the inner product of S and P times minus 2. And how can we describe this sphere K then? Okay, K, as we saw, is the center point P minus half radius square E infinity. That's a general formulation. And with this A included, the expression is simply P plus inner product S and P times E infinity. And then what is the final solution? We have K, we have S, and we are interested in the circle. We simply have need the outer product, and then this is the expression in order to compute the horizon circle based on the eye point and the sphere. Okay, I think this process was very geometrically intuitive and shows the power of conformal geometric algebra. It is very compact, because if you would do it conventionally, it is not possible to express it in simply one expression. And also nice is the role of coordinates, because until now we did not have to think about coordinates. This is only interesting if we would like to compute this with specific values. Okay. And how can we solve this now with GAALOP? These are the goals of GAALOP. We want to have an as much as possible easy development process. It should be possible to integrate it easily in standard programming languages. it should use this intuitive and compact descriptions based on geometric algebra. And at the end, the same goal as also Ahmad said, runtime performance and robustness. And I forgot reduction in development time, better maintainability. This comes from the very compact and easy expressions. Okay, this is GAALOP, the standalone version of GAALOP. Means we have two versions. One is running at the PC, and one is an online version of it. Okay, so this is the so-called GAALOP script. Means the algorithm to compute that in a practical way. So what we do in the first line is we use a function in order to translate the three Euclidean points into a conformal point to make it as easy as possible, but it is not a restriction. We say the center point of the Earth should be in the origin, means E0. Then we compute our sphere S with center point M and radius R. We compute this other sphere with this formula and intersect with the outer product. And then this question mark means please explicitly compute this C. We are only interested in the C. We are not interested in the other spheres. This is why we have this question mark. Okay, and then the result is very easy. So the circle, sure, it is a multivector, and GAALOP is computing only the multivector coefficients which are not zero. And what the meaning is indicated here in the comments. Means the first computation is the coefficient of E1 times E infinity. And then you see the expressions are very, very simple, only very, very simple expressions out of this more complicated expression that we have. Here you can see Ahmad already mentioned we have also the possibility to make common how is it called, sub-expression elimination. I don't know the correct word. You can pre-compute R times R at the beginning and then always use also this parameter. This is you can this is one of the no common sub-expression. Common sub-expression is the right word. Means R times R is a common sub-expression here, and you can pre-compute it. And you can see in GAALOP how you can configure GAALOP accordingly. Okay, and the nice thing is you immediately see we only need a very small number of computations, and our experience is that this leads also to a good robustness of the implementation. Because if you do not have, or let's say, more and more computations are more and more sources for inaccuracies, and this is why a short number of operations normally also means a good robustness of the computation. Okay. Okay, and this is the architecture of GAALOP. So you have your application where some geometric algebra part is included. Then we symbolically optimize the code, transfer it to a programming language and to different computing devices. So what we in principle do until here is we provide an internal description of your algorithm, which can easily be translated into different programming languages: C, C++, Java, OpenCL, GAPCO, Julia, Python, MATLAB, and so on, and you can go to different computing devices. Sure. What I would like to tell you concerning the FPGA solution, we currently have a specific solution in order to have an FPGA design able to understand geometric algebra algorithms. But Santiago yesterday told me that his solution is very, very easy. I thought that FPGAs have to be programmed with hardware description language, which is very specific, and I thought this is still so. But in the meantime, it is also possible to have that C code can directly be programmed on FPGAs. We had this discussion yesterday, and this helps a lot because this is a standard framework from the company AMD. And if you have a C code, he told me it is very easy to go to, or I saw it to the FPGA, which is very really a nice application. And for me, this means that if you would like to have a geometric algebra algorithm on an FPGA, a good idea is simply, okay, you can still work in MATLAB, can do everything in MATLAB first, then make your design with geometric algebra, include it in your MATLAB program as MATLAB code. And then if you say, okay, this part should go onto the FPGA, you simply can say, please do GAALOP, please do not generate MATLAB code, but generate C code. And then with this process with this framework of AMD, you simply can program the FPGA accordingly. And this is what I mentioned yesterday. If we have this kind of solutions, we somehow should present it in our center so that the people can easily find that, and we should document this in a good way, in order that people easily can understand how the process is. for instance, from MATLAB, generate a optimized solution, a GA solution for FPGA. And I have the feeling this would be the best for you. We discussed yesterday what we can do. Okay, I'm a bit sad because this means our ideas that I had with the Palermo people somehow we do not need that, and but I really like this way of doing it because it seems to be very, very simple. And the lesson I learned is that now I have the feeling that our solution is only an academic one. So we could prepare papers, but we publish in our community, and our community does not know that what industry people know, and this is why we can publish also the next years, but I'm not happy with it. so because I say now I know we have a better way, and we should do it like this. And this is why I'm sometimes why I'm feeling now that sometimes we are doing some research which is somehow behind what the industry is doing, and I'm not happy about that because I also teach my students with what I explained yesterday with Capco. But in principle, there's a better solution. And this is why I really think that the contact to industry is very, very important. And okay, I also think Jaroslav mentioned it yesterday. The personal contact is very important because the discussion yesterday, it was only possible because it was a personal meeting via online. I'm sure this would not be possible so easy. So this is why I think we should really think about where and when will be the next workshop. Okay. Oh, I'm a bit late. Okay. So I would like now describe the GAALOP pre-computation process a bit. So we are working with multiplication tables for the standard geometric algebras, but it is also possible to use on the fly computations. So this is, for instance, the table for the geometric product in 3D geometric algebra. Means we have our 8 elements, scalar, vectors, bivectors, and the pseudoscalar. And then our pre-computation works like this. You can see here the table entries are again all these basis elements, maybe with an additional sign, but that's all. And so you can see, for instance, if E1 is multiplied with E1, sure, the element is a scalar. And then our procedure is like this. We collect all terms where we see, okay, this is E1. And then we can see we have to compute A1 with B1 plus A2 times B2 A3 times B3, and this is the resulting code then. Oops. Okay. A nice discussion that I had 2 weeks ago with Harris in Cambridge was that we considered the complexity of geometric algebra computations if we have some operation which is needed in many dimensions, not only in 3D but in n dimensions. In this case, n is 3 means our multivector length is 8, but in general, the multivector has a length of 2 to the power of n, generally. And if we then consider that in principle, all for what was it, a geometric product, all the elements have to be multiplied with all the other elements in this table, then the complexity in this case is 2 to the power of n times 2 to the power of n, which is 4 to the power of n, means is exponential. And in this very simple case, we have 64 computations. And with GAALOP, we focus only on the elements that we really need. Means if we need vectors, you see, we only deal with vector elements and not with all the other elements. And this is why with GAALOP we need only 9 computations. 3 times 3. So this was a very nice experience, because this means we can reduce the complexity of a geometric product, which is in the worst case 4 to the power of n and exponential to n squared, which is polynomial. And this is really a big difference. Okay, some libraries can do the same with some specific amount of programming, but with GAALOP, it is very easy. So, and this means that we do a lot of pre-computations before we go really on the computer, and only a small amount is done really at runtime. This leads to fast and robust implementations. We already discussed this, and here is an additional optimization stage. Means in principle we have 2 stages, and also Ahmad discussed about how can we symbolically simplify expressions, and the easiest is to do it with some system which is able to do that, and we use maxima. So we compute our coefficients, and then we say maxima, please simplify these expressions. And that's all done before you really go to the machine. Okay. What's the problem? Okay. This was for the standalone GAALOP version. We also have this online version called GAALOP Web. Then you do not have to install something. So you, for instance, you have to install Maxima if you want to use the Maxima feature in GAALOP. But in this case, you do not have to install anything. You can go via GAALOP.de to this page, for instance, and GAALOP Web can use a visualization. So what we simply did is we use Ganja from Stephen de Koenig as our visualization. Okay, and then we currently have 3 servers where GAALOP Web is running. One in Darmstadt, Germany, one in Brno, and you also discussed a version which is running in Nanjing, China. And then you can easily select one of the languages you are interested in, and then this is the general screen. You can choose a geometric algebra, can describe your algorithm, and visualize and generate code for different programming languages. So in this case, we use a 3D projective geometric algebra. We can choose whether we are interested in code and visualization, or only in visualization, or only in code. I already mentioned this common sub-expression. We can configure it that we want to use it, and we can configure whether we would like to use maxima or not. Because the disadvantage of using maxima is that it takes longer. Oops. Sometimes I'm too fast. Oh, I see. Okay, so these are our standard algebras that we can use: imaginary numbers, Euclidean geometric algebra, projective, compass ruler, space-time, conformal, the geometric algebra for conics that Jaroslav already mentioned, double conformal geometric algebra, which is able to describe also quadrics, ellipsoids, torus, whatever. And 2 algebras for quantum computing, one our quantum bit geometric algebra and the quantum register geometric algebra. But I think the first one we do no longer need, or do we need it for some? Yeah. Okay. On the standard page, there are also some sample GAALOP scripts. And this is one example for the intersection of 3 spheres. This is part of the code here. You can see the variable assignment means you have to have concrete values for the center point of the spheres, for the radius, and so on. And then you can describe which multivectors you want to like to have visualized, and in which color. Okay. And this is the result of this 3 spheres example. So you can see the 3 spheres indicated with their variable names. You can play around with it, and here you can see the code. In this case, it is Python code, or the beginning of the code that you can use in your Python program. And the last page, it is an example of quantum computing, the 2 qubits NOT operation in quantum bit geometric algebra means this was our first attempt to describe quantum computing with geometric algebra. And what I realized this morning, we should change that, because in the meantime, we only use our new version, which is called quantum register algebra. And here no visualization is prepared. I really think that we should find ways in order to visualize also quantum register algebra. So you do not think that we need it, but for me it is important to have some visualization, because maybe mathematicians immediately see if the expression means this or that, but for me that's not so easy. Okay, and this concludes my my presentations. I only want to mention that there are some books describing GAALOP. The first was Foundation of Geometric Algebra Computing from 2013, then the Introduction to Geometric Algebra Computing, which was focusing on the two-dimensional compass ruler algebra, and my new book from 2022, The Power of Geometric Algebra, where I presented also things like, okay, GAPCO, quantum computing, or new possibilities for MATLAB Mathematica, Python, and whatever.
Thank you so much.
Thank you. Thank you very much.
We have some minutes for questions. First of all, I would like to thank you for this awesome example. So simple,
Yeah.
powerful geometric algebra. It blew my mind.
Yeah.
So I like it so much, and thank you for that.
Yes, it was really because yesterday you talked about this speech, and then I thought I should take this example.
It was a cool example, and it's a nice example of conformal geometric algebra. But I think it's important to be aware that an engineer or anyone would not be impressed by that example, because if I was an engineer and I wanted to find a sphere, I could just draw a right triangle, use cosine, and get the radius with another sine, and I could then have the circle parameterized, and I could do all this.
Okay.
I could do it in any language, and I wouldn't need to know CGA or use anything complicated. So it's a cool use of CGA, but if I agree with what you said before, that it's important to stay in touch with people solving problems that are real problems, because if you showed them this, they would not be convinced, or they would just think it's a more complicated way of doing a very simple trigonometric thing. But
really?
Well,
I do not know. For me, this example convinced me completely, because to be honest, I'm not happy to make all these steps that you have to do in conventional mathematics.
Like
it's not fun for me if I know that it can be done very easily.
I think it's important to at least sit down and try solving it directly, because it's but you're
Need another way of thinking.
And this is elementary for you. We will start from it's always the same. This is much more simple, but you need different background than is usual, and that's it. Yes, but you have a vector, and if you have H2 vectors, you have a plane, and if you are in T, you have a sphere, and then this is just introduction. This is just the sphere and the second sphere, and you have the result. It's almost the same.
If you are not convinced as an engineer of that, please look at the result, because I'm very sure that your engineer will not have the possibility to describe the complete implementation only with this very simple expressions, only 2 times px and so on. If you do all your steps, you always have to compute something. You have to compute many intermediate steps. But what we do is we directly compute the end result, and the end result is very, very simple, basic expressions. Yes, but you have to compute it. You have your library, and here we need maybe 10 multiplications, and in your case you have 100. That's the difference.
Dietmar,
I don't know.
I think we need to move to the next presentation. Maybe we can discuss
okay,
later
okay,
in the lunch.
Okay.
So thank you so much again. So our last presenter is Mr. Aleš Navrat from the Brno University of Technology, and also to end this day 3 of tools, the presentation is the geometric algebra for Quadrics. So Alex, the floor is yours.
Thanks. Welcome everybody. Thanks for. Sorry. Does it work or? Okay, sure. Just in the meantime, if you wonder why it is handwritten, so I'm definitely behind, you know, as you said it, behind industry. I'm behind computers, even. That's basic. That's mainly due to it was easier for me because I can hardly see without my glasses. So back in time. Go back in time. Okay. So thanks. I would like to introduce this. Okay, this topic. Actually, I forgot to write down the Peter's name, who is the leader, supervisor of Ludwig. Ludwig is his student, and this is his topic for his diploma thesis. And so he will talk about the implementation, which fits better to this block of lectures. But I will just briefly introduce like the topic. Yeah, and I wanted to stress that I thanks for the opportunity to be here. This nice event. I put a typical picture from San Jose.
Very different from the castle of Bird.
Another typical picture from San Jose. I could go on like this, but let's go to the topic. So I would like just to start with things that you know, everybody, but from slightly different point of view, maybe that you are not used to it. Then I will explain how to extend the conformal algebra to include more general objects like conics and quadrics. And then Ludwig will tell you about how he solved his problem with implementation of such high-dimensional algebra in C++. Twice. Okay. Okay. What? Yes. Okay. So I use the opportunity that I could draw pictures. So I just start with the vector algebra. So that's you can represent actually lines. So one-dimensional spaces you can represent, imagine as a line going through origin. And you everybody know that, yeah, when I take wedge product, it represents the two-dimensional space that it spans. So wedge products, by wedge product, I can generate objects, and by the dual to it, I can intersect them. So it really takes the blades and looks what the blades have in common, and it's actually the intersection. The dual mapping are orthogonal complements in the usual sense. By geometric product, I can compute reflections, rotations, in general. I can say orthogonal transformations, but it will be the same. This table will appear more times. So in PGA, one just takes go one dimension higher and take a plane, usually fixed coordinate to be equal to 1, and and in this way, in this say trick, I can, by the same scheme, I can represent Euclidean objects like point geometry. So just the line is which you get. The line is you obtain it as intersection of the plane that is spanned by the two vectors. So, but the same is true. The same table holds because you have these correspondence. It's still the same, but you have the correspondence between like the vector algebra and the point, in the point geometry. So, and it is similar, of course, in the case of conformal geometric algebra, which is crucial for. Okay, each time. Okay. 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 No, it's too much. Yes. Perfect. So here the correspondence is slightly more difficult, but it still could be understandable because it's already 2 dimensions higher. So one has to go to dimension 1 to be able to draw it somehow. And the correspondence is that now the points are the null vectors. This because I have this signature indefinite. I have vectors that have this length 0. These null vectors that span the cone, which is here, the blue cone. But actually it's the same. I have just different correspondence. I still have, so one vector is the line going through origin, but now it's a null line which lies on the cone. And this line represents a point in the sense that I have the cone. On the cone, can imagine this sphere and make a stereographic projection, and that's it. So, so that as it is drawn here. So the blue points there are actually the E naught and E infinity. So so that's the correspondence between points and vectors. And now I do the same, the wedge product. So basically, I'm still represent the objects by subspaces, by taking the blade. The blades represent subspaces, but in a bigger vector space, and the subspace cut something. There was a plane in PGA, now it's cone, and it cuts the cone. You can see it cuts the cone into this point pair. So the green and the red one, it's a point pair that it represents this blade. And the dual representation is actually, so you represent point pair or the sphere in general by the plane, or by the in this case plane, you know, and that's the blade actually. And in this case, for example, the inner representation would be the normal to the plane, so a vector that points out of the cone. So I think it's nice that you can somehow see the correspondence and what this conformal geometry, how it is made, the conformal geometry. That's really the picture. And you don't need coordinates. That's without coordinates at all. So, and you can do the same. You know, I didn't mention in PGA that you have to take it in dual, but it was written there. But now it's again the same. So wedge product, generate objects. In the dual sense, you intersect. Orthogonal complements are still like really the orthogonal complements, but here in the subspaces. But on the right hand side, it means orthogonal spheres, because it's clear. And the reflections, rotations, I mean, it's our reflections in spheres. So one has also the spherical inversions and so on. So it's a kind of geometric point of view that I wanted to show you. No, yes. I forgot. Okay, so now how to was maybe 2 slides. Okay, so I wanted just to show you what you know, how it looks in coordinates that you all know. So if you choose the right coordinates with this, where it has the form has this bilinear form has this form, you get the usual what you know. So the null vectors are exactly, it means this expression. So which means that the last coordinate which correspond to infinity is half of the square of the Euclidean norm. So it's the correspondence that I wrote in the recent slide in coordinates. So which gives you the usual embedding, as you know, but in a geometric way. Say. So now I have this embedding, and now I want to somehow include in this scheme more general objects. Say I will explain it on conics because for quadrics is very similar, and this is easier. So I have to add monomials to include conics. I had to have x squared and then y squared separate. So I have to I want to keep the conformal part. So what I have to add is the last but one term, which is difference of the two squares, and also the product to be able to cover also conics that are rotated somehow. But now how the way how, if I want to keep the conformal structure, what I need to, the two vectors that I add have to be null vectors, and so I need to them their counterparts. So we have E infinity to new E naught to new infinities, new E naughts, say. So that's how it is made, like artificially extending the conformal world. If I want to say the without coordinates, that's why this. So I still have the conformal cone of null vectors, but it's not enough, because now somehow these coordinates are bound together. So I have x squared minus y squared. So it's here. So the difference of the squares of these two coordinates up to the factor 2 must be this one. So it's like I have new cone here, or two new cones defined. So I can, without coordinates, I can view it as I have not the null cone, one null cone, but intersection of three null cones, say null cones, I guess. Yeah, but what is important is that the points are understand like they don't have these two coordinates. the green ones. So I have some subspace, blue subspace and green subspace, and what is between is exactly the conformal objects. But it's not. I mean, basically, to make the things work, one should rather think of these as a factor space, say, as a class of vectors that have on the first position not 0 0 but whatever, you know, like, so point is should be assigned to a class of vectors, and also conics should be assigned to class of vectors, and then everything works like before. By wedge product you can span the conics, so you take 5 points, you take a wedge of them, you get the conic, you can take the dual, so you can read of the internal parameters of the conic, you can intersect the conic, you can transform them. But what you lose is the orthogonality. The orthogonality from the outer space, the bigger one, does not somehow is not the right orthogonality. It's not the usual orthogonality. So you lose the concept of orthogonality, which makes things much, which is not good. But that's the price what one pays. Okay, so just I put this slide to if you want, yeah, the transformations. So how to, if you start with the embedding, so then you want to see what are the orthogonal transformation that makes the Euclidean transformation in the plane in this case. So for rotation, translation, scaling, say, so you search for a rotor that behaves like that. So the way is that you take a derivative simply, so then you get an equation for the generating bivector. So and the point is that these equations, the second line, this is linear. So this is a linear set equation. So you just solve it and you get the desired generator for the transformation you want. For example, for rotation, it looks like this. So the first term rotates as usual, and the additional terms somehow correct the additional pieces to make it work. Okay. Just a remark, you can have also consider, you can start with another embedding, and for example, this one, which is just change of variables, and you can get the same, similar, but with different representatives. Okay, and the last slide is the set about the quadrics. You can do perfectly the same, but now you have this is what Ludwig assumed. You start with the conformal part, but three-dimensional, and you have to add additional monomials to cover all possible monomials that you may have in quadric. So you have to add 5 next infinities and their counterparts, so the nulls. So it's pretty huge, the space, but everything works the same as in the case of the conics. Yeah, I should mention that originally the first paper was by Eckhart and the others, and they assumed more symmetric embedding, but again, as I said, it's just a change of variables. So you may, yeah, I mean, it does not make, it shouldn't make much more changes. It's change of variables. Okay, so it was just a remark, but you can do everything. So you can take 9, in this case 9 points. You can take them, wedge of them. You get the conic. You can, when you take dual, you have the inner representation from which you can read off the internal parameters, or vice versa. You can intersect the conics, but of course you get some wild objects. You can rotate, translate, scale. That everything works again up to the orthogonality. But the algebra has really big dimensions, so it's probably not so good for applications, but at least one should confirm, would like to confirm that it works. So in Ludwig's thesis, say, okay, he should also be able to implement it somehow to show that it works. So he will now he will tell you how he did it. So I give my word to Ludwig, if you are there.
Yeah. Yes.
Nice. I've been trying to switch my camera on, but I'm not sure if yes, hello this time. We will see if it works or not. Ask to be back. I will access as usual. Nice. So, hello everyone again. I apologize. I have my screen there, which I will be sharing in a moment, but my camera is there. But yeah, I will have to see what I'm sharing. So I'm sorry, but I have to move that way. So I would like to show you some, let's say, I call it a piece of code, which is capable of doing some calculations within the algebra, geometric algebra for conics. So times share. Could you please confirm that if I'm sharing?
Yes, we can see that. Perfect.
Yeah, very nice. To begin with, please understand that this was just a hobby project. It's not meant to be production level of code. It's not meant to be efficient, but it it uh, it is capable of doing what I need. So for me, it works, but it's slow, and I will get into that later. So as already indicated, the problem with this algebra, with the implementation, is the fact that the dimension is pretty high. So the main question is how to represent a multivector. So usually, the natural way of representing a vector in a computer's memory would be just to store an array of coefficients of basis elements in the linear combination. But here in this case, having such a big array, I just didn't like the idea. Also, I wanted quite good precision, so I didn't want to use just float as the type of the floating point number for the coefficient. So there was a problem. It would be pretty big on the stack memory, which has some limitations. So I came up with an idea that instead I would represent a multivector with a container map from the standard template library in C++, it's essentially an array of pairs, key, and its value, the key being, in this case, string, so the text representation of the basis element, and then the coefficient, in this case, yeah, this kind of floating point number long double. So this is the main class. It stores the generating basis E1 to En, in this case E15, and it uses for calculations not the null basis, but the pseudo orthonormal basis. So that's basically all I need to generate arbitrary element of my algebra if I implement the geometric product. And yeah, also it stores one as a vector, because yeah, we have this kind of scalar here as well. So
give you an idea, I want it to be easy to use and easy to debug. So I just defined these, well, they are just symbols, but they are basically shortcuts for me to pick the appropriate or the desired basis element I want to use for creating a multivector. So I will show how it works. You can see it's not, it's really a toy, a tool for me. It's not a library. It's really some hobby project which I'm having fun with. So then we can, first of all, I generate my generating blade. So I have E1 to E15, and I also have to include 1. And then the usage is just like this. Yeah. So this is the, I think it's a quite natural way to define an object of which represents a multivector. We have I implemented several operators. So of course the most important geometric product, addition, and then the rest follows like this. So it's capable of doing quite a lot of things. Also, we have this function up, which takes 3 Euclidean coordinates, and it's exactly, I can show, it's exactly the embedding which was shown. And yeah, here's E0, 1, then there is the Euclidean part, and then there is 1/2 of, yeah, this is just the second power of the Euclidean point with E∞1, and then the rest is, as was already shown. So that's roughly how it works.
Ludwig.
Yes.
Sorry to interrupt so abruptly. Could you perhaps zoom in the text a little bit so we can read the characters a bit better? Thank you. Perfect. Perfect.
Oh, I'm sorry. Is it better?
Yes.
Yeah. Okay. I will show one example. Also, you will find out how slow it really is, because the container map, it can dynamically grow, which means that there are a lot of heap allocations which make it really slow. So I will call this function rotation example. Just a second. I don't want all this. So in here, I define 6 bivectors, then I sum them, and that's exactly the generator for the rotation in the XY plane. Then I define the point C, which I want to rotate. Then I pick the angle of rotation. And also, I want to have a point to verify that it's that the calculation was correct. So that's just for verification, these 2 lines. Yeah, and then I can do, for example, the following as I do here. On line 32, I am actually computing the exponential by taking 20 elements of the power theory into account, and then the second parameter is the angle of rotation, and then I perform the rotation as expected. So if I run this, it will it will take 18 seconds. Yeah, so it's not very efficient, but it's yeah, it is what it is, and it works well for my purposes, just to verify that certain things hold. Yes, here we go. I will make it bigger. Just give me a second. Is it readable enough? Okay, thank you. So here I started with the point 1 to 3. When I used the embedding, the output or the result is as follows. And then I do the rotation, which yeah, sorry, I go here. So the result is this rotated point in here. I used for this line, I used the function down, which is in fact just the inverse of the point embedding. So that's also included, and the whole vector is in as in geometric algebra is written below, and then the target point is indeed the same. So I use sometimes this verification that I print also if the calculation matches. And yeah, you can see that it took 19.6 seconds. So yeah, it's pretty slow, but it's not pretty, but slow as hell, I would say. But it does the work for me. Maybe the last thing, just to demonstrate probably the geometric product. I will make it bigger in a second, but I need to find something. Yeah, here it is. Oh, it doesn't want me to. Yeah, here it is. So the way the geometric product is implemented, it does the calculation probably similarly to as a human would do it. So if I have these two vectors, then first I create a new map which contains these parts, and then I need just to simplify it according to the bilinear form which I have. So I use techniques. Just I have to separate the integers from from the text, and it's not the way it's not a good way, but it works. And to be honest, I never knew that I would show this to someone, so it was my secret. But suddenly there were people who find it very interesting, and yeah, please show it. And I'm like, oh, I don't like it very much. I'm not proud of it. But so here I am, just to give you an example how it works very briefly. But I don't have time to go to detail. But yeah. That's a, yep, that's all for my side. So I thank you for the opportunity, and I hand it back over to Mr. Navrat. So thank you very much.
We have only 15 minutes. The restaurant is waiting for us. So any question or?
Yeah, I have a question.
I have a question. Do you know the library of Leandro Fernandes in Brazil? He developed a library for high-dimensional geometric algebras, especially. To be honest, I do not know the details, but I know that it should be pretty good for high-dimensional algebras.
I'm not familiar with it. I know that something was, but I didn't do a lot of research in this because I really wanted to implement it myself as an exercise with just to just to exercise to be a better programmer, to know the tooling.
Library, maybe only to know about the principles of how this is working, because the approach has to be somehow completely different as what we are normally doing. And okay, it's just a comment.
Yeah, thank you. It would be, yeah, I'm definitely interested. Thank you.
Can I ask a question to Ludwig and Dietmar? So I already got an answer from Ahmad. I would like to know, can you also implement this high-dimensional algebra meaningfully in GAALOP, or is it too high-dimensional?
I think that's a question more on Mr. Hildenbrand. So
15 is possible. It depends on the RAM of the computer. So I do not know where the current limit really is. I think 20 should be possible, but currently not more. And we know that we have to somehow extend it for our quantum computing, for instance.
Sorry. Yeah, I think actually. Oh, sorry. Go ahead.
No, please, Ludwig, comment.
Oh, okay. I just wanted to say that I tried how many multivectors I can. If I do the representation with just the vector of coefficients, how many I can fit on my machine in a function in a stack, and it turned out quite many, like thousands of them. That I was really surprised. I didn't expect that.
Okay. That's really interesting. Yeah.
Thank you, Eckhart. I don't know if there is another comment. Maybe Joseph.
Sorry for so many questions. Do you actually need many dimensions to express a simple Euclidean rotation? Do you just need the three dimensions, the three Euclidean dimensions, or do you need?
It's a silly question. Yeah, but you need to add the parts to correct the the movement of the other external parts. So it's somehow yeah. So it's yeah, but it is like I wanted to express it. It's also to find out where still are some benefits and where are already limits. It's exploration. It's mathematics rather than a solution for industry.
I have another question. Maybe it is also a question to Eckhart, because he is very experienced in that field. There's also the double conformal geometric algebra, which is not so high dimensional, and in principle you can also describe quadrics. So what is the reason for using this algebra then?
Isn't this algebra has the advantage that it's a perfect analogy to conformal geometric algebra. That means you can intersect all objects and use all objects also for reflection or rotation, etc. And you have some limitations in double conformal geometric algebra. You can, in double conformal geometric algebra, only use basically, you can construct these more general objects. It's super hard to do it, but you cannot use them generally to reflect any object at any other object.
Okay, so we have some extra minutes for the last part of the workshop, which is the integration, closing remarks. So I don't know if any of you have some comments on the integration part. Maybe some of you. I mean, the integration between the different libraries. So the idea was to present these different libraries, and maybe there is a chance, so there is a. I saw some potential collaboration and benefits between you are. There are two of creators. Also, Ahmad, which is another creator, and I think it'd be a good idea to stay in touch and to benefit from each other. Try to enrich the different libraries. Try to um, maybe to find a niche for the application. Maybe some of them are so general. Maybe some another are so specific. I don't know. So it could be an interesting idea to get in touch with you and try to collaborate in order to enrich all this panorama. Okay. So I don't know if Ekar or Ahmad has any comments. If not, maybe we can close the session. Yeah. Yes, Ahmad.
Okay, I can suggest an initial step from me. I can make a more detailed video on how to use metaprogramming in GA-FuL. Not for the purpose of GA-FuL itself, but the ideas might help others developing their own libraries. For example, in the last talk, instead of using the names of the basis vectors as keys in the dictionary, we can make it more efficient. I already did that in my work to use scalars or integers, and the code to manipulate the geometric product on the basis plates is already done in C#, so you can transfer it in your C++ library. So this is my suggestion from my side for now.
Thank you.
Yeah, thank you. I agree. It's a good idea. Should be definitely possible and many times faster than.
So, can you hear me?
Yes.
Yes. Okay. So my comment, I don't know if there's a real closing or something. First of all, I want to thank the local organizers very much for organizing this workshop. And like from today, I would say I learned, because so far I thought that quadratic conformal geometric algebra is algebraically really nice and you can do many good things, but at the moment all the platforms are too slow to work with it, or they wouldn't produce results with reasonable accuracy of the coefficients, etc. But now I see with the various contributions today that there may be light at the end of the tunnel, and this algebra may eventually come to fruition. And, I mean, to manipulate quadrics or sets of quadrics. There are so many applications in natural science, I guess also in engineering, that this would be really interesting, I think.
Okay. So I think we can conclude our workshop. I did not prepare any words. Yes. Only to say thank you to every of you. I hope that apart from the wind, you find this place as a nice place to stay. I hope that our company, the launch, the dinners. I hope you stay pleasant here. And I have something to comment on this. Isia commented that he's available for any other meeting or workshop or whatever we decide to celebrate in the future. He offers Barcelona, and of course, I think Sebastian will also be available. But you know, Isia is in direct connection with Manel and Arnau, which is another electrical engineer in the group. And the other thing I want to mention is that Santiago wrote me very quickly. He told me that, and this is something that I've read sometimes, that MATLAB can also generate FPGA code directly. it has an HDL tool. So you can write your code in MATLAB and it looks like it can generate FPGA code directly.
Yes, sure. But our idea was to use optimized geometric algebra code.
Yeah.
And then you need that.
Okay. No, this is the words of Santiago. So that's all from my side. So thank you for your presence here, and we will see very soon. We need to decide where, if maybe in person or hybrid, I don't know. And it's time to go to the restaurant and try to launch. So thank you, Eckhard. Thank you, Ahmad. Thank you, Ludwig. So see you soon, but in person, please.
I hope so. Yes.
I also really enjoyed it.
Yes, goodbye.